So here is an exercise for the method of joints for you to practice, and we have some information about the framework. You can see the supports here and calculate the reactions at A and at C. Calculate the tensions then in the 5 members. I'm going to call them things like TAB, TAC, etc. So have a go. Don't watch the video as such, try and solve the problem. The answers are on the next slide, and after that I go through the details. Okay, welcome back. Let's look at the answers. So here are the reactions at A and B, and the tensions with the notation I mentioned a moment ago are given both exactly and also to 2 significant figures, and I'm also saying whether they are in tension or in compression, and since TAB is in tension, if this is minus TAB, this is in compression, and TBD is the same as TAB, so it is in tension. Okay, congratulations if you've got it right, and I go through the solutions on the next few slides. Okay, to solve this problem, because the members have all got the same length, we're going to have equilateral triangles, the angle being 60 degrees, and then we're going to need a little bit of geometry, and these are the values of the trig functions that we will need. This is a good thing, in my opinion, to know. So the first step for the method of joints, work out the reactions. This is a roller. That means that the reaction is straight upwards. There is no horizontal component. Here there could be a horizontal component, but the sum of all the horizontal forces has to vanish. This load is vertical, so this is the only possible horizontal force. It must be 0. The sum of the vertical forces is also going to be 0. This is 20 kilonewtons downwards. The sum of these two forces must therefore be 20 kilonewtons upwards. To work out how this is divided between them, we take moments about a point. In my opinion, the simplest point to choose is about A. That way we will get rid of the contribution of R1, and we will have contributions from the load and from R2. The distance for R2 is 4 meters, the length of one of the members, and the perpendicular distance for the load is going to be 4 plus 2, half of this distance. So this is going to be anti-clockwise. It has a positive moment. This will be clockwise about A. It has a negative moment. We just rearrange that and we find that R2 is 30 kilonewtons. This tells us that R1 is going to be 20 minus 30 when I take it over there. So R1 is minus 10 kilonewtons. In other words, the reaction is downwards. Okay, that's step 1. The remainder of the problem is to find the tensions in the individual members. So I've just drawn the diagram again and been explicit about what the reactions are. And the key idea is you draw free body diagrams of the various joints. So I can draw a joint here or here, and the first thing that we have to do is realize let's choose the simplest first. So supposing we drew the free body diagram at C, there would be 1, 2, 3, 4 forces, only one of which we know. We're going to get 2 equations at any joint, so we're going to have 3 unknown forces, 2 equations. We're not going to be able to solve for these forces yet. It's much easier to look at, let's say, A, or to look at, let's say, D, because at these 2 joints we have 2 unknown tensions and 1 force here 20 kilonewtons, 2 unknown tensions. I'm going to choose as A. Let's look at that on the next slide. So, the free body diagram at A, we have the reaction downwards, we have the tension here TAB. I'm assuming that all of the tension or all of the members are in tension, so I'm just drawing them this way. If we get a negative sign, we'll know one's in compression. And you can actually look at this and see one of them must be in compression, because as it's currently drawn, both of them are acting to the right. This is acting vertically downward, so there's nothing acting to the left. So it must be the case that one of these is acting to the left. Let's find out which one by solving the problem. Vertical forces first, because this has a vertical component and this is known. So it's going to give us a nice simple equation. The vertical component of TAB is either TAB times the cosine of 30 or TAB times the sine of 60. That's the same thing. So let me just write TAB sine 60 upwards, and then it's minus 10 kilonewtons acting downwards. They must sum to 0. We take the 10 to this side, divide by the sine of 60. We know what the sine of 60 is. This is our result for TAB, written that way, or if you prefer, you could multiply top and bottom by the square root of 3 to write it in this format. Okay, we now know what TAB is, so this tells us that TAC is going to have to be negative to balance the horizontal component of TAB, which is acting to the right. Let's see how that works. So TAC plus TAB cos 60 are going to have to sum to 0, and we know what TAB is. We just substitute this number in, we rearrange, and we obtain that TAC is minus 10 over root 3 kilonewtons, where I've used that the cosine of 60 is a half. So now we know these two tensions, and we know that this member is in compression and this member is in tension. Let's move on to another joint. So now we're going to choose the next joint to draw a free body diagram, and what I would suggest is we still don't choose C because there are 4 forces involved. So we could choose B or D. In both cases there are 3, and we know one of them in each case. We know this, and we now know TAB. So let me just choose B. Here's our free body diagram. TAB, TBC, and TBD. We know the value of this, and let's just draw the angles carefully. If I drop a perpendicular vertical line here, I'm going to bisect this angle, which is 60 degrees, so I'll have 30 degrees here and 30 degrees here. This is a vertical line, this is horizontal. This total angle is 90 and this is 60. That's the angle here in this equilateral triangle. And similarly, this is 60 degrees. So the sum of the vertical forces is going to be 0. So we have TAB times the cosine of 30 plus TBC times the cosine of 30. I'm adding them together because they're both acting in the same direction vertically, they're both acting downwards. Now we look at that and we see that the cosine of 30 is a common factor you could pull out, so we can cancel that common factor, and we recognise that this equation just tells us that TAB plus TBC is 0. So TBC is minus TAB. And since TAB was 20 over root 3 kilonewtons, TBC is minus 20 over root 3 kilonewtons. Good, that means we have solved for this. What about horizontally? Well, the forces acting to the right are going to be TAB times the cosine of 60 here. But then this, because it's negative, is actually acting in this direction. So its horizontal component is TBC times the cosine, or minus TBC, times the cosine of 60. In other words, the horizontal components of this and this double up. So we get 2 TAB cos 60. And acting in the other direction, which has to balance it, is TBD. So these terms are going to cancel each other. So TBD, take it to this side, is 2 TAB times the cosine of 60. Cosine of 60 is a half. The half and the 2 are going to cancel. So TBD is the same as TAB, and it's 20 over root 3 kilonewtons. So we've now calculated the tensions in all three of these members, and TBD we see is positive. In other words, TBD is in tension. Just a quick comment on that previous slide. So if we look here at B and we say, well, we've got 60 degrees between these two members. This is in tension, this is in compression, and this is also in tension. And if we say that there is no load at B, which is the case for this exercise, then the sum of these three forces have to be 0. Now I can just say that the line of action of this just carries on upwards that way. So this corresponds to this. And the angle between these two is this, 60 plus 60, 120 degrees. And if I just draw this one straight up here, then you can see that this is symmetric about the dotted line continuing this line. So it would be 60 plus 60, it's 120 degrees as well. And this angle here would also be 120 degrees. So this is like a Mercedes star. And the only way that we can say that the sum of these three forces in all possible directions vanish is going to be if they're all the same. So this symmetry tells us or explains to us why the magnitude of these three tensions are exactly the same. Okay, we've now calculated all of the tensions in the different members, except for TCD that we still need. So what's the simplest choice? Well, I'd say the simplest choice is to go to D, draw the free body diagram here at D, and we have a horizontal force here, and a vertical force here, and a force at an angle of 30 degrees between this, and 60 degrees between this and this. So the simplest thing, I think, is just to look at the vertical forces. So we have 20 acting straight down, and we have plus, because this is downwards at the moment, TCD times the cosine of 30, this angle here, and that's got to be 0. Looking at the sum of these two things tells you TCD is going to be negative, so this is going to be in compression, and we just rearrange it. TCD works out to be minus 40 over root 3 kilonewtons, and that is in compression. So now we've calculated the forces in all of the members, and I've just got a couple of comments about possible checks. So there are a few checks you could still make. If you remember our free body diagram at D, we only looked at the vertical components of the forces to work out what TCD is. We've got TCD, we've got TBD. We can check that the sum of the horizontal components vanishes. It must be the case if we haven't made a mistake. Similarly, if we go to C, we draw the free body diagram there. We've not used that at all. Is it the case that the vertical forces sum to 0? is it the case that the horizontal forces sum to 0? Well, on the next slide, let's just look at this. Horizontally, we get this equation. Check it. And the cosine of 60 is a half. Remember the numbers we had. TBD was 20 over root 3 kilonewtons. TCD was minus 40 over root 3 kilonewtons. Multiply this by a half. You'll get minus 20 over root 3. And add that to the plus 20 over root 3. They cancel. So we see that the sum is 0 and our check is working. So your turn. Check at C that both things work. The sum of the horizontal forces is 0 and the sum of the vertical forces is 0. And then you're really confident that you've got it right. I hope this has helped you.